Hello, Algebra 2, ladies and gentlemen. You're probably wondering why Mrs. Brennan's voice sounds different today, but this is Miss Marr, and I'm actually going to be doing my first flip video with you guys, and it's on the exponential growth and decay real-life examples. You guys worked on graphing exponential growth and decay functions with Mrs. Brendan yesterday, but now we're going to be doing real-life examples. So what you're going to need is your guided notes, which you hopefully already have, a pen or pencil, and a calculator. And with that, let's get started. All right, so we're going to start with an exponential growth model. And so for when if you guys remember from yesterday, you guys were graphing the function y equals a times b all to the t. And when b was greater than 1, you called that an exponential growth model. So now we're just replacing b with 1 plus r, and we're going to call 1 plus r the growth factor. So that's why it's a growth model, is because r will still be, 1 plus r will still be greater than 1, so that's why our model will be growing. So a represents the initial amount, or what you started with, and then r is the percent increase. When you're doing growth models with real-life examples, you're going to look for words like increase or appreciate or go up or build or something like that, something to signify that it's increasing. And we want to make sure that our rate is always expressed as a decimal when we write it in the equation. So we would have the percentage divided by 100. And then t represents our time. So let's look at an example of exponential growth. So let's write right away our equation before we forget. Y equals a times 1 plus r all to the t. There was an initial population of 38 buffalo in a state park. The population is growing 7% each decade. Write an exponential growth model and estimate how many buffalo are in the park after 70 years. So we're going to start with y equals, and our initial population of buffalo was 38, so that's going to be our a. And now we're looking for our rate, which is 7%. And as a decimal, that is expressed as 0.07. So we're going to say 1 plus 0.07 all to the t. Now, what do you think t is? I know a lot of you are tempted to write 70 years as t, but let's take a look back at our rate. We said it's 7% each decade, and a decade is 10 years. So over 7, if we want to have our t correspond to our rate, then we need to know how many decades the rate is increasing by. So 70 years divided by 10, which is a decade, we would get 7 decades. So our t is actually 7. So let's type that into our calculators, and we would type 38 times the parentheses 1 plus 0.07 parentheses caret all to the 7, and we would get an answer of 61.01, and then the decimals would keep going. So remember, these are real life examples, and we're talking about buffalo. We can't have a 0.01 part of a buffalo, so when we're looking at our answer, we need to round to the whole number, which would be 61, and then always remember to include your labels. So we will look at another example. We are going to be looking at compound interest now, and this is an example of exponential growth. We use this model when we're not compounding yearly. So the last equation we just looked at was if we were to look at per year, and now we're talking about compound interest as something that's increasing more than once a year. So our equation is a equals p times the quantity 1 plus r over n all to the power of n times t. P is the initial amount deposited, or what we started with, and then r is our interest rate, and remember that we want to express this as a decimal, so the percent over 100, and then n is the number of times compounded per year. And remember, this is more than once a year, so it's either semi-annually, quarterly, monthly, weekly, or daily. Semi-annually would be twice a year, quarterly would be 4 times a year, monthly would be Yep, 12 times a year. And then weekly would be 52 times a year. And then daily would be 365 times a year. Then T is going to be the number of years that we have this interest growing. And then A will be the balance after T said years. So let's look at an example of compound interest. And let's start with the equation. We said A equals P all times 1 plus R over N all times N, or to the N times T, excuse me. So you deposit $2,900 into an account that has 0.35% annual interest. Find the balance after 2 years if the interest is compounded monthly and weekly. So our N for monthly would be 12 and our N for weekly would be 52. So we're going to be writing 2 equations and finding 2 different answers. So let's start with the monthly. We're going to start with A equals our initial amount P, which is $2,900, all times 1. And let's remember what our rate is. It's 3.5%, which expressed as a decimal is 0.035. So let's come back down to our equation, 0.035. And remember, we're doing monthly, so all divided by 12, all to the 12 times, what was T again? Oh yeah, 2 years, 12 times 2. So let's type that into our calculator. Oh, excuse me, I'm getting ahead of myself. I was going to do the next question of monthly. So let's type that into our calculators. It'd be 2,900 times parentheses 1 plus parentheses again 0.035 divided by 12, all to the 12 times 2, or 24. And we get an answer of, remember this is money, so 3,109, and since it's money, we're going to be rounding to the hundredths place, and that would be 96 cents. So that's our answer for monthly. Now let's do for weekly. So A equals, our initial amount didn't change, so that's still 2,900, and our rate didn't change, so that's 1 plus 0.035, but we are now doing it weekly, so we're going to divide by 52, and it's all to the 52 times 2. So let's type that into our calculator, and we're going to be typing 2,900 times parentheses 1 plus parentheses 0.035 divided by 52, all to the 52 times 2. And our answer is A equals $3,110.20. That's interesting. When we compounded monthly, it was $3,109, and then compounding weekly only gained us $1. So that's interesting to see that within 2 years of compounding monthly and weekly at such a low rate of 3.5%, we only gained $1. So now let's look at an example of decay models. So like the last one we had, like we were graphing, you had y equals a times b all to the t. Well, now with a decay model, remember that when you decay, b is less than 1. So we're going to have b be the same thing as 1 minus r, and we're going to call 1 minus r the decay factor, just like we called 1 plus r the growth factor. This is the decay factor. So a is the initial amount, and then r is the percent that decreases. So when you're looking at a decay model, it'd be decrease, depreciate, goes down, words like that. And remember, we want the rate to be expressed as decimal, so it's percentage divided by 100. And t is time, as always. Depreciation, now we're looking at a depreciation example or an exponential decay example. A new car, oh, excuse me, let's start with writing our equation up top so we don't forget. Y equals A times 1 minus R all to the T. A new car costs $25,000. The value of the car decreases by 23.5% each year. Write an exponential decay model giving the car's value Y in dollars after T years. So we're going to just write our equation with T years. So we'll still have T in our equation. So let's start with that. Y equals our initial amount, or our initial cost was $25,000 times 1 minus R is our rate, and we said our percentage was 23.5, so our rate, remember, we want to express as a decimal, so that'll be 0.235 all to the T, because we wanted just a model. We aren't actually finding a value yet, but now we are estimating the value after 4 years. So we're going to start with our equation Y equals 25,000 all times 1 minus 0.235 all to the 4th. So let's type that into our calculators. 25,000 times parentheses 1 minus 0.235 all to the 4. And our amount comes to, our value comes to $8,562.21. So that is a pretty quick rate that it's depreciating, that our car is depreciating that fast, because when we first bought it, it was worth $25,000, and now we're saying it's only worth $8,000. So that's a lot. So not all cars depreciate that quickly. The rate can sometimes be lower than that, but remember I said that there are also real-life examples of appreciation. So with a car, you might think that all cars depreciate because people use them, but classic cars appreciate because they're classics. So they actually gain money the time they're just sitting in parking lots or being driven around on Sundays or something. So that is all I have for you, and I will see you tomorrow.